This is going to be the free response questions from the 2019 test. So let's go ahead and go over this real quick. So I got question number 1. It says, identical blocks 1 and 2 are placed on a horizontal surface at points A and E respectively, as shown. The surface is frictionless except for a region between points C and D where the surface is rough. Beginning at time TA, block 1 is pushed with a constant horizontal force from point A to point B by a mechanical plunger. Upon reaching point B, block 1 loses contact with the plunger and continues moving to the right along the horizontal surface towards block 2. Block 1 collides with and sticks to block 2 at point E, after which the 2-block system continues moving across the surface, eventually passing point F. So it says, on the axis below, sketch the speed of the center of mass. That's the key. So we're looking at it's a 2-block system. So we got 2 blocks in this, so we want to look at the center of mass of both of them. As a function of time from time TA until the block passes point F at time TF. The times at which the block 1 reaches points A through F are indicated on the time axis. So what you're given here is something like this. And then we got time. And you have TA, TB, TC, TD, TE, and TF. All right, and then you got some like random grids. I mean, it doesn't really matter. It doesn't really matter because you're not going to have, it's not really labeled numerically. So it's just you need to show what's kind of happening. There's no actual like values to it. Okay. So let's look at point A to point B. So what happens is that it's under a constant force. So the velocity obviously is going to increase from point A to point B. And since it's under a constant force, it's going to have a constant acceleration. So how we show that on a graph, the speed is going to continually increase. That should be a straight line. Let me undo that real quick. There's going to be a straight line somewhere to point B. You can pick one of the cross sections to point it at and then just draw a straight line up. All right? So at point B, it releases from the plunger and it's moving. And there's no friction during B and C. So if there's no outside forces, there's no acceleration. Therefore, it's going to be moving at a constant speed. So you're going to keep that at the same line. So there to there. So it should be straight, horizontal, because it remains at the same velocity. So then we look from C to D, there's going to be a frictional force. It's going to apply a constant force when it's going across point C to D. So again, friction causes the velocity to decrease. So we're actually going to have decreasing, and how it's going to decrease is at a constant rate. So another straight line. Now, the key here is it's not going to stop because we know that it's going to hit block 2. All right, so eventually it has to hit block 2, so it has to have some velocity after it leaves part D. So therefore, I can't make this line go all the way to 0 because then it would stop and never reach block 2, which we know it does. So again, just pick another point, somewhere down here and draw it right there. So D to E, right before it hits, we know that it's not there's no friction. So at point E, I know it's gonna be here. Now, here is where it gets a little confusing, okay? We're talking about the center of mass. So a lot of people are gonna try to do this, like when initial momentum is gonna be conserved here, and if we're doubling the mass, we're probably gonna half the velocity. So what a lot of people might do is they're going to draw something like that, okay? Well, that's not correct because we're talking about the center of mass. This would be accurate. This right here drawing would be accurate for if we were drawing the velocity of block 1, all right, throughout time. So let me undo that. Now, what was I going to say? So when we look at this, velocity can only change if there's on a system, on the center of mass. Okay, now keep in mind, we have a 2-block system. All right, there are external forces. In this part right here, the beginning part right here, is the plunger. Gives you the external force. No external forces here, that's why it stays constant. There's an external force here, it decreases. All right, no external forces here, it stays constant. Now, if I think about this, right, we're talking about the collision of block 1 onto block 2, right? So let's think about the forces that are in action here. Block 1 is hitting block 2. Block 2 is pushing on block 1. Newton's third law, equal and oppositely. So if I have a positive force and a negative force, they cancel out. All right? So if there's no net external force, that means the velocity is going to remain the same. So therefore, it should remain that way. So how you got to think about it is, one is going to lose velocity, right? But that velocity it loses is gained up by mass 2. So that's why the center of mass velocity stays the same. All right, so that's going to be okay. Go to the next part here. Let's see. Let me go ahead and clear this. This is 1B. So now it says the plunger is returned to its original position and both blocks are removed. A uniform solid sphere is placed at point A as shown. The sphere is pushed by the plunger from point A to point B with a constant horizontal force directed toward the sphere's center of mass. The sphere loses contact with the plunger at point B and continues moving across a horizontal surface towards point E, in which intervals, if any, does the sphere's angular momentum about its center of mass change? Check all that apply. All right, so, first thing we need to do is that we have to know, so it's saying angular momentum changes, right? Yeah. The sphere's angular momentum change, yeah. All right. So when I look at this, we have to remember that angular momentum is conserved if there's no net torque acting on it. So in other words, if there's no torque and no net torque, the angular momentum is going to be conserved. So we have to figure out the points along the path, so A to B, B to C, C to D, D to E, if there is a net torque on it. All right, so let's just kind of look at the forces. So let's consider forces. All right, so obviously there's going to be a normal force acting on the sphere. Well, at what points are the normal forces acting on that sphere? Well, it's the entire time. So that goes from A to E. Now, when thinking about the normal force, right, I got it here, it's going to be pushing up from there towards the center of the sphere. Well, does a force in that direction cause a net torque? So no, it doesn't. No torque. So no, I'll just leave it at that. So no torque, no net torque from the normal force. All right, next force I got is the force of gravity or weight. Well, weight acts on it the entire time. It goes from A to E. That's going straight down. This force is through the center of mass, so there is no torque. So there is no change in angular momentum. All right, let's see, force of the plunger. That goes from, let's see, A to B, right? It goes from A to B. Now, the key here is the force goes directly through the center of mass. You're pushing straight on. Causes no rotation on that one. So there's no torque, no change in angular momentum. The last is force of friction. Goes from C to D. So if I look at the sphere when it's rolling on the friction, right? The friction is going to oppose a force this way at the place of contact, right? Or a force acting in this direction on a sphere is going to apply torque onto the sphere. So therefore, angular momentum is not conserved through this portion. And so you're going to want to check C to D. Okay? So that's B. Is that it for that question? Yeah, that's it for that question. So let's clear on here, and then let's go to number 2. All right, so I'll real quick, just so you kind of see what's going on. I got a tabletop, we got pulley block going over. This is B, this is A. All right. So it says this problem explores how the relative masses of two blocks affect the acceleration of the blocks. Block A of mass MA rests on a horizontal tabletop. There is no friction between block A and the tabletop. Block B of mass MD hangs from a light string that runs over a pulley and attaches to block A, as shown above. The pulley has no mass and spins with no friction about its axle. The blocks are released from rest. AI. So AI. Suppose the mass of block A is much greater than the mass of block B. Estimate the magnitude of the acceleration of the blocks after release. Then it says briefly explain your reasoning. So what I have here is that block A is going to have so much more mass than it's much greater than block B, right? So really, block B is going to be pulling with a really, really small force as compared to the mass of block A. So the tension trying to pull it is going to be relatively small, all right? Now, block A, because it's so massive, right, is going to have a lot of inertia, so it's going to resist that move. So if you're talking about something that has a lot of inertia and only a small force acting on it, all right, it's not going to move. So what we can say it's going to move because there's no friction. But since it's such a small force, we can say merely 0. Mass A, so this is your explanation here, has a great amount of inertia, resist motion, tension from B is very small because it's the force of gravity on block B. Okay? Clear that. Well, let me erase this because I'll leave the drawing. All right, so that's a I. See what A, I. So now suppose the mass of block A is much less than the mass of block B. So it's basically the opposite scenario. Estimate the magnitude of the acceleration of the blocks after release. Briefly explain your reasoning without deriving or using any equations. So you don't want any equations here, just kind of concepts here. So block B has a lot of mass compared to block A. So block A is going to, so let's think about this way. If there was no block A and block B was just falling, it would have acceleration due to gravity, right? It would be going at 9.8 meters per second squared. It was in free fall. So there's no friction on block A, and there's barely any mass as compared to block B. So it's gonna take away some, but since it's so small compared to block B and there's no friction, what we can say is it's gonna be nearly 9.8 meters per second squared. Okay, it's going to be nearly in free fall because the force resisting it is just barely anything. Okay, so it's basically the exact opposite of AI. Okay, make sense? All right, good, clear. That makes sense. Like you can answer. Stupid. All right, so this is 2B. All right, so now suppose neither block's mass is much greater than the other, but that they are not necessarily equal. All right, the dots below represent block A and block B as indicated by the labels. On each dot, draw and label the forces exerted on the block after release. Represent each force by a distinct arrow starting on one and pointing away from the dot. All right, so I got block A, block B. Got two dots here, right? So what's key here is this. You don't want any components, just the actual force and the direction. So if I think about block A, the one on the countertop, all right, you're obviously going to have force of gravity, or you can call it weight of A. You want to denote that. You're going to have normal force because it's on a table, and you're going to have tension force. All right. On block B, you're going to have tension force pulling up. Then you're going to have force of gravity of B, or you can call it weight of B. All right. There's your two free body diagrams. Pretty simple, pretty straightforward. That one's pretty easy. All right. Let's go ahead and keep going. I'll erase that. Hopefully you write that down because we're gonna come back to it here in a second. It's pretty easy though to remember. So what is this? 2C. So now it says derive an equation for the acceleration of the blocks after release in terms of MA, MB, and physical constants as appropriate. If you need to draw anything other than what you've shown in Part B to assist in your solution, use the space below. Do not add anything to the figure in Part B. So once you answer the question, don't touch it. Use a different space to do your work. So all this work I'm going to do right now is away from that drawing on the dots because you don't want them to confuse work for Part C for your answer for Part B. All right? So let's draw it real quick. Normal, weight, tension. So what you remember when we did these problems, right? I'm going to do a summation of the forces equals MA. You can do this as an entire system, right? We ignore external forces because they're going to actually cancel out. And I look at the forces that are in the direction of the acceleration, right? We want to find the acceleration. Well, if you look up here, there's no other forces in the direction of the acceleration. So what I have to look at is down here, this block's moving up and down. Oh, the only force in the direction of the acceleration is going to be the weight of block P. So what I'm going to do is I'm going to set this as a positive because the blocks are going to accelerate that way, so my acceleration will also be positive. And when I look at this, I can do this. I go mass B times gravity, which is weight, equals, now it's the total mass of the system, so I have to do mass A plus mass B times acceleration. And let's see, they want you to solve for acceleration, and you get mBg divided by that quantity, MA plus MB. There's your equation. All right, so I'm going to keep that up because D kind of asked about that. So what D says is this. It says, consider the scenario from part A2 where the mass of block A is much less. So this is block A is going to be much less than block B. Remember, we had a acceleration that was nearly G, right? It was nearly acceleration due to gravity. does your equation for the acceleration of blocks from part C agree with your reasoning in part A? So we're going to see, does this equation here make sense to our reasoning in that part here? So if mass B is these masses here are so much greater that effectively mass A does not even affect it, right? If I look at this, what's same thing over the same thing, because this is so small compared to these, it doesn't affect it, all right? MB over MB is just 1, so 1, and the only thing left is going to be my G, so acceleration is like G, so you would click yes. And you have to explain. Yeah, you have to explain by doing the same thing I said. Look at the thing. A base essentially goes away, and then MB over MB is just 1. 1 times G is your acceleration due to gravity, and it's almost the acceleration due to gravity. All right, so let's clear that. Good deal. And this is 2E. It says while the blocks are accelerating, the tension in the vertical portion of the string is T1. Next, the pulley of negligible net mass is replaced with a second pulley whose mass is not negligible. When the blocks are accelerating in this scenario, the tension in the vertical portion of the string is T2. How do the two tensions compare to each other? Briefly explain your reasoning. So let's look at, so same thing, same exact drawing. I'm not going to draw it again. Let's look at block B. So if I do just the forces on block B, right, I have, what do I have? I have, is that going to be T2? What's it say? The tension in the vertical position of the string is the tension of the oh, okay. So that's it. Yeah, it's going to have T2. So basically, block B is going to look like this: T2, force of T2, and then weight of B. So what I can do is I got MBG down positive minus T2. Equals MB, and we're only dealing with block A. So if I solve for tension, I want to see how tension goes here. FT2 equals MBA. Oh. Undo that. Oh. Let's see. I got to subtract over, then I get the negative. So I have MBG minus MBA. My equation I'm going to look at, right? So what's going to happen here is that the acceleration of the system is actually going to go down. Acceleration is going to go down because of the mass of a pulley, right? So now you have to take in that consideration. So if the mass is going to go down, I mean the acceleration here is going to go down, that means the tension in that is going to go up, and therefore it's going to be greater than T1. So the correct answer here is going to be T2 is greater than T1. There's what's it called? There's your answer to E. All right, and that's it for number 2. Let's keep on moving. 3 says a projectile launcher consists of a spring with an attached plate, as shown in figure 1. When the spring is compressed, the plate can be held in place by a pin at any 3 positions, A, B, or C. For example, figure 2 shows a steel sphere placed against the plate, which is held in place by a pin at position C. The sphere is launched upon release of the pin. A student hypothesizes that the spring constant of the spring inside the launcher has the same value for different compression distances. The student plans to test the hypothesis by launching the sphere using the launcher. AI. State a basic physics principle or law the student could use in designing an experiment to test the hypothesis. AI. Using the principle or law stated in part AI, determine an expression for the spring constant in terms of quantities that can be attained from measurements with equipment usually found in a school physics laboratory. Let's see here. So what we could do, what you're going to do here, you see the spring. So there's a couple different ways you could do this before. So we could think about it like this. Let's think about it like this. You could launch the thing vertically, right? And you could measure max height. All three. You could, what else could you do? You could basically have it on a table and you could shoot it horizontally and measure the distance here, a maximum delta X for all three positions. So you're horizontally going to launch it out like that. Or you could just launch it horizontally and have one of those motion detectors to get the velocity of the ball. All right, so there's kind of a couple different options here. I think this is the easiest one because it just gives you the value that you need right away. So I'm going to work with this, but kind of the same thing here. So this, if you're going to say launch it vertically, this would be the conservation. So it asks for what principle. So this would be the conservation of mechanical energy. This would still be conservation of mechanical energy and projectile motion. And this one is just conservation of mechanical energy. Whatever you want to use, that's what you're going to do. So I'm going to go from here. I'm going to use this one. So that's AI. So I'm going to do AII. So this is 3 AII. Says using principle or law, so determine expression for the spring const. Oh, we need an equation here. So I'm launching. Let's draw it out here. Horizontally, I have a motion detector here. That's going to get me when it leaves that thing. What's its velocity here? So this will be the final. And then the initial is just it compressed. So in other words, what it looks like in figure 2. So if I do this, mechanical energy initial equals mechanical energy final, I'm going to set this height, whatever it is, because it doesn't change, where potential energy equals 0. So you don't have to worry about potential energy because it stays at the same height. Now, looking at this, so look at figure 2 because that's going to be our initial. It's compressed, it's not moving. So it doesn't have kinetic energy, it doesn't have potential energy. All it has is elastic, it doesn't have gravitational potential energy, it has elastic potential energy, which is equal to 1/2 K. Second half, so this is the final, look at this picture. We're looking at the instant that it leaves the launcher. So in other words, it's not in contact with the spring anymore. So 0 spring, 0 gravitational potential energy. It only has kinetic energy, 1/2 mv squared. All right, there's our equation. We want to solve it for K to get something that says K equals. This is velocity final, and this is your initial position. So I'm going to get mv final squared over the initial position squared. So the halves cancel out. Okay. There's our equation for number 3, AII. Keep that in mind. We're going to come back to that here in a little bit. So let's keep going. Yeah. 3B. Design experiment procedure to test the hypothesis in which a student. So we needed to design an experiment and then fill out this chart or something. All right. So let me write this equation up here so you can see kind of what we need. So K equals mvf squared over xi squared. So that's the equation we derived. So we're going to come back to that. So it should be obvious that we need mass. So first thing we should do is measure the mass of the sphere. So in quantity measured, just say mass of sphere, symbol for quantity, M, and equipment you need would be like electronic balance. Okay, so write that. I don't have room for a chart. Just write that down. So then what we said is we're gonna turn launcher horizontal. Okay. So then what you're gonna do is get equilibrium distance of spring with meter stick. So you want the starting point. Where is the spring at when you're at equilibrium? All right. So next you're going to come next. Oh, I want to write next. Compress spring to one of the pin placements. Now we want to measure distance that it was compressed with meter stick. So I would write your initial position, in other words, compressed position, is your symbol XI, symbol for quantity, quantity to measure initial displacement from equilibrium, and equipment used for measurement is your meter stick. All right? So then you're going to release sphere. Use motion detector to measure velocity final. So symbol for quantity would be velocity final. The equipment is going to be motion sensor, and then quantity to be measured is final velocity of the sphere. Now, what you need to do in here is this. There's a let me see. Let me get this. Let me get the wording right here. Okay, so B continues on the next page, and I forgot to read it. It says, describe the overall process used to test. So the key here is provide enough detail so the student can replicate the experiment, including any steps necessary to reduce experimental uncertainty. So you need to add steps to cut down on experimental uncertainty. So we really haven't done that yet. So what we can say is do 4 trials at all 3 pin placements. All right. So there, we're gonna cut down our experimental uncertainty with more trials. Okay. So that should be our procedure. Again, you could do a procedure for any of them, any of the 3 ones or whatever. I'm just doing one for the sake of time here. This is C. Says, describe how the experimental data could be analyzed to confirm or disconfirm the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances. All right, so let's look at our equation here. Easiest way to confirm is using graphical data and the slope. So if I look at this, remember that slope equals rise over run. So if we want K to be the slope, all right, this is going to be our rise and this is going to be our run, right? So on the y-axis, we're going to graph, and then on the x-axis, we're going to graph. Okay? Now, when you graph that, okay, if your line of best fit fits the data, all right, in other words, it's linear, right? and goes to 0, 0, the origin, all right, then the spring constant is going to be equal. It's going to hold true for your hypothesis that the K value is the same no matter how far you compress it, okay? Should be pretty, that should make sense. Now, if it doesn't fit, then therefore the K value is going to change, all right? So that's C. I'm going to go ahead and D, you have this. And launch speed. All right, so it says, another student uses a launcher to consecutively launch several spheres that have the same diameter but different masses, one after another. Each sphere is launched from position A. So you're setting the position, in other words, the X value the same. The K value is the same, so that's going to be a constant. What you're changing now is the mass. So each sphere is launched from position A. Consider each sphere's launch speed, which is the speed of the sphere at the instant it loses contact with the plate. On the axis below, sketch a graph of launch speed as a function of the sphere's mass. So again, let's start with the equation we derived. Now we're looking at velocity. So let's solve it for V. You can do the algebra. You're going to end up getting VF equals square root of K I squared over M. So remember, these are constants, right? The K value is not changing. We're always shooting from position A. So in other words, we can just write it as 1 over M, right? So in other words, if I got a graph that looks something like this, all right, my graph doesn't matter, square root, whatever. It's going to look something like that. All right, hopefully that makes sense. We can set this to 1 because these stay the same. It doesn't matter. The only thing that's changing is your X variable, in other words, your mass. All right, as your mass increases, all right, your velocity is going to decrease. That's exactly what this graph here says. All right, so that makes it done for number 3. And then number 4. So this schematic drawing here I got. So that's what I got here. Let me read it. A motor is a device that, when connected to a battery, converts electrical energy into mechanical energy. The motor shown below is used to lift a block mass M at a constant speed from the ground to a height h above the ground in a time interval t. The motor has a constant resistance and is connected in series with a resistor of resistance R1 and a battery. Mechanical power, the rate at which mechanical work is done on the block, increases if the potential voltage drop between the two terminals of the motor increases. Determine expression for the mechanical power in terms of M, H, and T, and physical constants as appropriate. All right. So what we need to do here is just remember that power is any change of energy in whatever amount of time. And if we look at, in this case, energy is equal to how much work is done on the system. All right? So when I look at this, let's look at initial. So if we set wherever the block initially, so we look at the total energy here. If we look at the initial spot, it's at rest, so its velocity is 0. Okay, so it's 0 kinetic energies. You know, its potential energy, initial, is going to be 0. Okay, so total energy here is 0. After you do the work on it, still not going to be moving once you get to the top. Once it finally gets to the top, it's not going to be moving. So 0, but it's going to have potential energy equal to that. So our change in energy is going to be equal to the potential energy it has at the top. So if that's our change in energy, all right, is equal to this, that's equal to the work done. So what I can do is I can use this knowing that the change in energy is equal to that. In other words, the work done by the motor, that's how much it changed the energy of the box. So therefore I can plug that into there. So I get power equals the change in energy is equal to M, the mass of the block, G, constant, and the height of however high I went divided by the time it took to do that. So there's my equation for A. All right, that's pretty easy, pretty straightforward there. Let's clear it up. For B, look here, it says, without M or H being changed, so M and H are going to remain the same, so the height and mass. The time interval T can be decreased by adding one resistor of resistance R2, where R2 is greater than R1 to the circuit shown above. So why don't I erase it? I'll draw it real quick. Motor. All right. How should the resistor of resistance R2 be added in the circuit for time to decrease? In other words, we want more power because we want the time to decrease, right? If we remember our equation, this stays the same, this stays the same. We need this to decrease, so this has to increase, right? We need more power. In other words, we need more current flowing through that motor. So we have a resistor R2 that we need to put in this so that we can get more current through there. The only way to do that should be pretty evident here, is that if we put it in parallel with R1, so watch how I do this. So the total resistance, we know R2 is greater than R1. So let's just say, for example, R1 equals 2 and R2 equals 4. Right? That holds true for that. So the total resistance in this up here is going to be 2. Ignoring the motor because the motor stays the same in both. Right? So there's 2. If I look here, I add total resistance, or equivalent resistance, I got 2 over 4 plus 1 over 4 equals 3 over 4. I gotta take the inverse, I get 4 thirds. In other words, I get 1 and 1/3, which is less than 2. So the total resistance here is less than 2. That makes the current is going to go up, therefore getting more power in the motor, thus decreasing the time. All right, hopefully that made sense. Pretty straightforward. That one was kind of easy, I think. All right. Next, moving on to number 5, last one here. All right, so we have a tube. Open, length L. Tuning fork, I'm not drawing that. A. Oh, we want to know length of the tube. All right, so it says a tuning fork vibrating at 512 hertz. So I know the frequency of the tuning fork. So, all right, I'll draw the tuning fork. So I know the frequency is 512 hertz. It is held near the end of one tube length L that is open at both ends as shown above. The column of air in the tube resonates at its fundamental frequency. So fundamental frequency is, so we know it has to start antinode and end at antinode. So the fundamental frequency would look something like that. Antinode, something like that, all right? So if I do this, I know that that's half a wavelength, right? So I know the length equals wavelength divided by 2, or you can write it as wavelength equals 2L. There's the equation we're going to use. So, and it says the speed of sound is, so I know the velocity of sound in this medium is 340 meters per second. All right. Last equation we need is velocity is equal to lambda frequency. So length of the tube, I can just plug in here. So I'll use this. So I need to plug in for lambda. So I solve this for lambda. I get lambda equals your frequency. Plug that in there. So I get length equals. Go ahead, solve. Length is what I'm looking for. V is, what is it, 340? Frequency is 512. When you do that, you get 0.332 meters. Again, pretty easy, pretty straightforward. You just got to remember antinode to antinode allows you to make this equation. You need to remember this equation here, plug in, solve, and then plug in your numbers. All right. B. Max speed, particle speed. And I got 4, so 304 L. All right. So again, let me draw the tube up here. All right. So at the end, so if you have a problem like visualizing it because it's sound in a tube, again, you can do the same thing with waves on a string. Just think of node and antinode, okay? So at an antinode, all right, even on waves of a string, right, you got the string, these are the nodes, right? So this goes up and down, right? Max velocity at the antinode, that's max velocity of the string. So it's the same thing. At the antinode, that air is max velocity at that point. Again, it has like 4 things here. It's not labeled, or you mean the number's not there. But no, it's at the maximum at the antinode. At the nodes, in other words here, all right, it's basically zero movement, right? Nodes are zero movement. Think about this on a string, zero movement. So the air is has zero movement. So I can do that at halfway point, right? Okay. And then at the end of the tube here, again, it's going to be max velocity. So I go up here, max velocity. The velocity of the air is going to follow the same path as the what's called the actual sound wave, right? Because it's going to increase as it goes. It's going to increase velocity. As I'm going on this, it's increasing velocity, right? So in other words, if I start at a node and I go towards, it's going to increase velocity until it hits its maximum velocity. So it's going to follow the same kind of wave as that. So it's a sinusoidal wave. So it's going to be the same thing here. So I'm going to come down. Should look something like that for our particle speed. All right, so that's B. Says now the right end of the tube is now capped shut. So I'm going to draw it. This is capped shut. So this has to be a node, and I'm going to antinode. Antinode. All right, so I write my new equation here. I know that's a quarter, so the length of the tube equals a quarter of the wavelength, or wavelength equals 4L. So there's the equations we're using. Again, I just got those from looking at the picture I drew. All right. Place in a chamber that's filled with another gas in which the speed of sound. So our new speed of sound is going to be 1,005 meters per second. Calculate the new fundamental frequency of the tube. So it's the same length, so our length here is going to be 0.332. We want to know the fundamental frequency, so in other words, off of this one frequency here. So yeah, we can just plug in. So again, what I got? V equals, I want to know frequency, so I got to get frequency in there. So again, I can solve for lambda. I need to plug in right there. So I got plug in velocity, 0.05, frequency. And I go ahead and solve, and I get somewhere. Pretty straightforward on that one. All right, hopefully that helped. That's the whole practice, the free response for the 2019 AP Physics 1 test.